50% higher than the pre-industrial era. Prior to the industrial revolution, as I explained to you, up to 1900, it was not much. As such, the temperature was not increasing, and all of us are aware because of the carbon dioxide emission concentration in the environment, this temperature increases there. And the major issue is to reduce the carbon dioxide concentration in the environment, basically in the ambience, and that is how we'll have to do it. Presently, if you really look at the world average of the carbon dioxide emission on 2020, as per the Climate Watch, is around 34.34, and India is emitting around 24.56 gigaton or a gigabillion. The giga ton, what we call GT, what we call it as. And in addition to the direct carbon dioxide, there are other gases like CH4 as well as nitric oxide, etc. Though there, like the pollution intensity of these other gases is very high, it doesn't stay in the environment for a long time. It vanishes up very fast, whereas the carbon dioxide, remains in the environments for thousands of years together. Once it gets accumulated in the environment, so that's it's very necessary, essential for us to bring it down. Though India is emitting around, as you can see here, around 7% of the world carbon dioxide emission to the environment, but it's a moral and the ethical responsibility of us to participate here and bring down the carbon dioxide emission to the environment, or the carbon footprint in the environment. Where do we stand as a construction engineer? It is said that the 42% of the carbon emission is because of the built environment. As you can see here, out of this 42%, around 27% basically is because of the operation of the systems, like the ventilation system, and in case of the buildings, running the pumps for lifting the water to the top of the buildings, and this sort of things. This is called the operation carbon, whereas the embodied carbon, I'm just going to explain to you, and the rest is because of the embodied carbon in case of the buildings, whereas the infrastructure, the operation carbon is almost negligible. I would like to differentiate between the building sector as well as the infrastructure sector over here for the purpose of that. Out of this 42%, almost 100% of the cement production goes into the construction, basically, and almost around 59% of the steel production goes into the construction, and the aluminum around about 41%. Basically, the aluminum is only 1 gigaton, that is around 1.5% aluminum is sort of consumed in the industry, basically in construction industry. That's around 0.41 gigaton, this one. Out of this 42% of the carbon dioxide emission to the environment, if you convert that, 19% is because of the concrete or the cement, what we call it as, 14% of the steel, and 2.7% is because of this, what we call it as aluminum, and the 64% rest is because of the operation carbon, what we call it. Now, let us try to understand the terminologies which are used, embodied carbon and operation carbon, etc. All of us are aware that very famously our Prime Minister Modi announced the Panchamrita to bring down the carbon to the net zero by 2070, basically in two phases by 2045, 45% by 2030 as well as 2070. To certain extent, it has been achieved too, basically. Now, I use the two terms. One is the operation carbon as well as the embodied carbon. Operation carbon is nothing but energy-centric operations in the building, like that the running of the lifts, water pumps, and the common lighting and use of household appliances such as fridges, washing machines, etc. is called operation carbon. And almost, if you really look at it, as I explained to you here, 64% of the carbon emission comes due to the consumption of the energy in the building sector, whereas in the infrastructure like bridges, it is not, operation carbon is very less. It is not much, because to run the bridge, You don't require, only perhaps the lighting is required. Apart from that, much is not required. But other in-use carbon dioxide emission is going to be very high in case of the infrastructure. So it balances out as far as the building sector and the infrastructure is concerned. Now, what is the embodied carbon? Embodied carbons come from the direct emission during the process of production and the consumption of embodied energy consumed to extract, refine, process, transport, and fabricate a material or product in this one. When the production of, say, for example, the cement takes place, due to the chemical reaction, some carbon dioxide emission directly takes place, and also a lot of energy is required for the production of the cement. That is energy is called, consumption of that energy is called the embodied energy. When for the right now, on the basis of the state of the art technology which is available, the electricity is produced, maximum electricity is produced by the burning the coal. Actually, while burning the coal, when the electricity is produced on the basis of the current state of technology, almost around 0.71 kg carbon dioxide equivalent, 197 kg carbon dioxide equivalent gets emitted for production of the 1 gigajoule. That's why the consumption of the embodied energy while producing the cement or the steel also gives rise to the carbon dioxide. That's why the embodied energy concept is also very important. All over the world, if you really look at it, BSEN, the life cycle stage, a model which has been provided by the 15978 2011 is universally used. This is for the building sector, as you can see here. Within the whole life cycle stages, at different stages, the carbon dioxide emission takes place, as you can see here. During the production as well as the construction stage, it is called the upfront carbon, or the before the use carbon, and the from the in-use carbon is when the facility is being maintained, and during the service life, whatever the maintenance as well as the intervention is required, whatever the carbon dioxide emission is called the in-use carbon. And once its service life is over, say for example, in case of the infrastructure, 100 years the service life, and the buildings right now are designed for the 50 years, but it's going to be designed in future for the 75 or 100 years. During the service life, and whatever the carbon dioxide emission takes place, it's called the in-use carbon. After that, it has to be demolished, and while after the demolition, as well as the transportation of the demolished materials and the dumping, the carbon dioxide emission, which is it is called the end of the life stage carbon, that is represented by the 4 modules, as you can see here, C1 to C4. And the concept of the circularity, I will come to that later. And it's also, defined by the boundary systems, what we can call it as cradle to gate. Up to the product stage, cement is produced, steel is produced. That is what is called the cradle to gate up to the production stage. And after that, the construction takes place. Transportation of, say, for example, cement has to be brought from factory to the location of the construction. And after that, using the cement, the concrete is being produced, and the concrete is poured into the molds, and all this called the construction. This also, the emission of the carbon dioxide takes place. Then that is called the cradle to completion. And you have, after the in-use stage, cradle to grave, as you can see here, cradle to completion. Then up to this end of this, like the end of the structure, it is called the cradle to grave. And if the circularity is used, whatever the materials or the components of the structure, which if it can be reused it once again, then it is called the cradle to cradle. So this concept we will be we'll be discussing going forward. That was for the building sector, as you can see here. This is for the infrastructure. If you really look at it, in the infrastructure, we have got additional modules like A0. A0 is the preliminary studies as by the consultations and the clients. That is called the A0, whereas in the building sector, it is not there presently in this particular model. Even in the in-use state, there is a user's utilization of infrastructure and other operational processes, say, for example, if you can take. That is the difference between this building sector as well as the infrastructure. We have got 3 additional. So we have already defined what is the whole life of carbon, and the total carbon dioxide emission during the service life, including the production of the facility, whatever it's including the demolition of the facility, is called the whole life cycle carbon, whole life carbon, as you can see here. Now, I have tried to give you here a model of my own for the carbon neutrality, as you can see here, which I call it as a years model, which has an estimate, avoid, reduce, or the setup. And I would like to define this carbon neutrality is a process where greenhouse gas emissions are brought to net zero by avoiding. And if it is not possible to avoid, by reducing. If it is not possible to reduce, then setting it off. Whatever it's not possible to reduce, set off that. So by doing that, if you achieve the net carbon to the net zero, the carbon is achieved. That is what is called the carbon neutrality. And this is the model which we are going to study today. And this model has, as I told you, that there are 4 stages. One is the estimate, then the avoid, then the reduce, as well as the setting off. And the estimate stage, as you can see here on this this slide over here, and it has to be done during the different stages in the whole life carbon, and the methodologies of the estimation has to be there. Cradle to gate estimation has to be done. Gate to completion is the construction, that is A4 to A5. Completion to grave estimation is called in-use stage, basically the estimation. And finally, grave to cradle estimate. That also includes the circularity. If it is used back, it is plowed back. The same construction materials, construction components, if it can be plowed back and the reconstruction can be done, what we call it a circularity, that we are going to discuss. Now, what are the methodologies of calculations of the embodied carbon? What we call it as a carbon factors. Basically, how does the carbon embodied carbon is calculated? We have a carbon factor for a cement, say for example. That carbon factor is multiplied by the cement quantity. Then you get the embodied carbon, that kg carbon dioxide per kg cement, or the ton carbon dioxide equivalent per ton of the cement. Similarly for the steel and other construction material also, there are very famous guidelines are available how to calculate embodied carbon. It has been very regularly referred for the building sector basically, and this gives the guidelines. And also the inventory of the carbon and energy, that is the carbon factor, what we call it as, which is the multiplying factor for arriving at the carbon dioxide emission to the environment. And it has been brought out by Building Services Research and Information Association along with the University of Bath. As you can see here, these are the 2 very important documents for the carbon factor. And as I told you that carbon creation is happening during the different stages. As you can see here, this is before the use stage, and this is the in-use stage. In case of the infrastructure, 100 years this facility is designed for, and this design of the structure is done for 100 years, but certain performance level will get reduced. As the performance level gets reduces, you will have to intervene here and repair the structure, rehabilitate the structure, make the performance level go up again, and again it comes down. So several interventions are required, and also the maintenance of the facility for the 100 years is required. That is how in use stage carbon dioxide emission also takes place basically. Now, during the product stage, that is the module A1 to A3, we have got a carbon factor. I have just compiled the carbon factor, which is available in India on the basis of my experience in working in the construction industry. This carbon factor has been multiplied, as I told you, for the different materials. It's a very simple, like for the cement, how much, aggregate, how much. Suppose if you are using for the fly ash, if you are using the reinforcement steel or the pre-stressing strands, even the structural steel, all these carbon factors are available. That has to be multiplied with the quantity you will straight away get. Similarly, for the in case of the construction, normally what do we do? How do we do the construction? During the construction, fuel consumption of the plant and equipment takes place. Construction, when you are doing, you are using the equipments, and also during the construction, wastage in materials takes place, and also we use the enabling and the temporary structures. The carbon dioxide emission because of this has to be worked out. Basically, all this requires what? The fuel consumption. So you have got some carbon factor for burning of, say, for example, for running this generator that the DG set, you require around 9 liter of like fuel. For example, that 9 liter of fuel, because suppose if it's consuming 9 liter of diesel, for consumption of 1 liter of the diesel, almost the 2.7 kg carbon dioxide equivalent is carbon dioxide emission takes place to the environment. So we can directly multiply this fuel factor, fuel consumed during the construction stage. That's how the construction stage, this embodied carbon is being calculated. Most important thing is you have to see that in case of the what is the embodied carbon? If you really look at the embodied carbon in the construction industry, basically it is the capital carbon of the embodied carbon which is taking place. And in case of the concrete is being produced using the materials, and the cement, the concrete production takes place using the transmit mixers as well as the batching, and that is transported to the transit mixer. Pumps is being used, and that is how the concrete finally gets into the mold and the concreting takes place. That is how the concrete. So in a built environment, most carbon emitting material is the concrete as well as the steel. If you really look at it, say for example, in the product stage as well as the construction stage, it has been all over the world, it has been recorded, whether it's the building sector or the infrastructure sector, 2 to 4% carbon dioxide emission takes place because of the consumption of the fuel or the electricity which has been used for running the equipments. 40 to 50% carbon dioxide takes place because of the production or the process of the production of the steel as well as the cement itself is concerned. Whereas even in the new stages, if the intervention is required by way of the repairs and rehabilitation and the maintenance, like I'm going to explain to you, you may have to replace the overlay or you may have to do some repair work. All this is where the steel or cement is consumed over here. So basically, if it's possible for us to control the carbon dioxide emission because of the cement and steel and bring it down to net zero, in construction industry will be able to achieve the net zero by 2070 as has been laid down by Indian policymakers. Now, look at the cement. Cement almost emits around 0.8 ton carbon dioxide emission, and steel emits around 2.5, on an average, whether it's reinforcement steel, pre-stressing steel, or the structural steel for that matter. And it has an embodied energy of around 5.5 gigajoule cement, whereas the steel has an embodied energy with the current state of technology which we have is they talk about 20 to 30. I have taken around 30. Now, if you look at the concrete, basically, even in the concrete, 87% is because of the cement again. So again, I come back to that. The cement and steel is responsible for emitting the maximum carbon dioxide into the environment in the built environment, basically. That is almost around 90% of the carbon dioxide emission takes place because of the cement and steel. Even the demolition is around 1 to 2%. Construction is around 2 to 4%. Rest is because of the maintenance as well as the intervention. As you can see here, 30 to 60%. And in case of infrastructure, there is no operation carbon here. It's only this one. But the infrastructure, we have seen that the bridges have to be replaced within 100 years, 40, 50 years. There's again a spike in the repairs and rehabilitation of the infrastructure. Sometimes the bridges have to be replaced. That will again ended up with the heavy spike in the carbon dioxide emission, as you can see here. So by controlling the cement as well as the steel carbon dioxide emission to the environment, I think we'll be able to achieve the dream of our Prime Minister to achieve the carbon dioxide emission to the environment to net zero by 2070. That's how my presentation goes on. Similarly is the case with the steel. And if you really look at the fabrication is nothing but the steel construction, basically fabrication and erection. If you really look at the percentage of the embodied carbon in the production of the steel itself is concerned, this is a steel plate over here. This is the rolled section, and also there is the cables as well as the strands. This is because of the fabrication, as well as the erection, it's only hardly minuscule of embodied carbon during the production of the steel itself. So we have to control this 40 to 50% production stage, also the in-use stage. In-use stage, whatever the cement as well as the steel which is going on for the repairs and rehabilitation, if we are able to bring down, the net zero will be able to achieve this. How do we calculate carbon dioxide in in-use stage? In-use stage, as I said, if the facility is designed for 100 years, as you can see here, we'll have to maintain that, right? And maintenance will be, maintenance regime has to be defined. What we do in the maintenance, replacing of the wearing coats, resurfacing of the deck. Similarly, for the building sector also, we can have a maintenance regime. All this will be we will end up with the carbon dioxide emission. And if the performance is going down, actually this performance has to be brought up. It has to be refurbished or rehabilitated and in fact, some cases it has to be replacement has to take place, and the capacity increase has to be done. Again, when the capacity augmentation is to be done, carbon dioxide emission has to be taken place. In case of the infrastructure, even during the construction, even during the repairs and rehabilitation, the traffic diversion may have to take place. When the traffic diversion takes place, like only the small portion of the deck is or the carriageway is allowed for the traffic to be moving. There will be a deceleration zone, queuing zone, as well as the acceleration zone, and again the acceleration zone, and it's called the work zone. Average speed will be reduced for stopping, queuing, as well as this one. The additional carbon dioxide emission takes place because of the additional use of the fuels, the renewable fuels or the fossil fuels over there. And because of that, again, additional carbon dioxide, that is called the user utilization carbon, user's carbon. And also some cases, this traffic diversion may completely avoid this particular bridge itself or the infrastructure itself. And that infrastructure itself, and in that case, the whole traffic diversion takes place. And the traffic diversion, when it takes place, the length of the distance to be traversed or it will become more. Additional carbon dioxide emission takes place because of that. That is also for the user carbon. Now we have seen that how to calculate, estimate the carbon footprint at the different stages of the whole life cycle of a facility over here. Now the next is after the estimation, the avoidance. I think this particular like this arrow is in the wrong direction, and the avoidance should have been basically there down. The avoidance has to be there. And how can we avoid it? The complete avoidance of cement and steel completely, whether it's possible, that we'll have to have a look at it. Avoidance of non-renewable energy consumption in construction and operation. Instead of non-renewable energy, renewable energy sources, which is not out of the fossil fuels, which is not because of the burning of the coal. If we are able to make sure completely avoid it, it's possible for us to do that. Here is an example. I just taken an example for the purpose of that. I've taken an infrastructure example, a bridge girder. It's an ASTO standard bridge girder of around 37 meter, which has been using the regular reinforcement as well as the pre-stressing strands, and also the normal concrete, like the regular concrete of M60 grade of concrete, it has been designed over here. And for that, for cubic meter of concrete, like that, if you really look at it, 1.3 ton carbon dioxide emission take place for the conventional girder. If you completely avoid the metallic reinforcements, say for example, if you go for a FRP bars, for fiber reinforced polymer bars or the aramid fiber reinforced, it could be aramid, it could be glass, it could be carbon. If you go for that kind of a strands as well as the steel, and also the cement, which is the zero cement, it doesn't have the, when I say zero cement concrete, it doesn't have the OPC at all. That kind of cement, this has been done abroad, and if it's possible for us to replace this OPC as well as the metallic, the reinforcement completely, it is possible for us to bring down this carbon dioxide emission to 0.4 ton carbon dioxide per meter cube of concrete. This is almost around 1.3 to 0.4, it's around 70%, as you can see. But it is not so easy because presently the state of the art technology is for the pre-stressing strands. It's not in the form of a strand. It is a straight bar. It's like a tension bar, and also the FRP bars are there, which can be used for the construction. But those bars, unless a lot of research is done, and those bars can be bent at the site and the way we want, and it can be used. Presently, it has to be ordered. It is the order specific. That's the reason that technology has to be changed. I think, but it's possible for us to completely avoid the cement as well as the metallic reinforcement, as you can see here. Then another issue is while producing the cement, as you can see here, it emits around 0.8 ton carbon dioxide direct emission, but it has an embodied energy of 5.5 gigajoule, whereas the steel has an embodied energy of 30.0 gigajoule. That including this embodied energy consumption, the carbon factors is for the cement is 1.084 ton carbon dioxide equivalent, whereas for the steel it's around 5.9 ton carbon dioxide equivalent. So by completely switching over to the renewable energy source, such as like the biomass energy, solar energy, wind energy, hydro energy, nuclear energy, perhaps it is possible for us to completely avoid this carbon dioxide emission because of the renewable energy sources like fossil fuel energy as well as the coal energy, as you can see here. The cement and steel factories may be mandated to have their own captive power plants of renewable energy sources, and they may be mandated to have the green hydrogen, clean hydrogen for the purpose of production of the energy. But the hydrogen again has to be produced using the energy, the renewable energy sources like all this energy. But if you are producing the hydrogen using again this fossil fuel energy, again we ended up with the carbon dioxide emission. This is a complete avoidance of carbon dioxide by eliminating completely the energy source itself, making it a renewable energy source, as well as completely avoiding the OPC and metallic reinforcement in the concrete. I think it's possible for us to, but it's not so easy. It's easily said than done. That is why if it is not possible for us to completely avoid, the next step in our model is the reduction of the carbon footprint, reduction of the OPC content in unit volume of concrete, reduction by use of alternative steel to carbon steel, reduction of heat wastages during production of the steel and cement, because this generation of the heat, it is used, up to 1200 to 1600 degrees, both in the production of the steel as well as the cement. That requires the energy which comes out of the fossil fuels or the electricity which is made up of coal burning again. Reduction by waste production, composition, upgradation of the plants, reduction of intervention during the service life, reduction by resilient structures because of the climate emergency. More and more resilient structures are required going forward. Reduction by the design efficiency, reduction by the design for circularity, reduction of wastages during construction, reduction by policy making. These are some of the steps which can be adopted. The global strategies for the net zero in steel and concrete construction is as you can see here. As per this, the basic material industry emission trajectory for 2020-2050 by World Economic Forum. As you can see here, they are targeting globally to reduce this embodied carbon of the steel from 1.9 ton carbon dioxide emission, carbon dioxide equivalent to almost around 0.11 ton by 2050 by phases. As you can see here, by 2030, they are planning to bring it down to 0.92. Presently in India, it's around 2.5, but the global average is around 1.9 ton carbon dioxide emission for production of 1 ton of the steel. And if it can be brought down to 0.11, I think that is what the globally all these global players are estimating it to do it. That's what the target is. Similarly, in case of the cement, though in India for production of 1 ton of the cement, it requires around 0.8 ton carbon dioxide emission takes place. Globally, it's around 0.6 right now, and the global target is to bring it down to 0.03. And if it is a global target, using the same principle, if we use in India also, instead of that, if you can reduce this direct carbon dioxide emission in from 0.8 to 0.3, I've taken 0.8 to 0.3 instead of 0.03. That's only 62.5%. Globally, they are almost around 90% they are doing it. If I'm taking 62.5%, the direct carbon dioxide emission will reduce from 13 to 8, 8, and the balance will be around only 5 ton carbon dioxide emission takes place, 5% carbon dioxide. Decarbonization energy by 50%, from 83, it will be come down to 41.5. I think you can bring it down to balance left is 41.5. During the transportation and construction, fossil fuels is used. There also, if it's possible for us to decarbonize, decarbonize in the sense you will have to use the renewable energy source rather than the non-renewable energy source. I think if it can be brought down for 40%, I think balance left is around 2.4%. This balance left has to be reduced by design for circularity, by reuse and recycle at the rate of 20%. That is what I call it as circularity. So this 96%, 83 plus 13%, out of this 96%, even 20% by the circularity design, if it can be brought down, 19.2% carbon dioxide emission will be able to bring it down. And design efficiency by 20%, if it is possible for us to bring down, around 19.2% carbon dioxide emission in case of the concrete structure, will be able to bring it down. Balance, which cannot be really reduced, whatever is left, I think that can be used for CCUS, what we call it as a balance by carbon capture, utilization, storage, and sequestration. Cement as well as the steel industry has been doing a lot of research in this direction to do that. In fact, they want to do it carbon capture, utilization rather than the storage, which cannot be utilized in the form of converting this carbon dioxide, capture carbon dioxide into some other material and make use of that some other material in other productions. That is called the carbon capture and utilization and the sequestration. And if it is not possible to do it, I think we'll have to be sink that into the ground. That's how the 10.5% can be done. This is what the proposal is for the concrete, how it can be reduced. This is how I put it in the form of a diagram or the pictorially, as you can see as strategies is design efficiency saving, circular economy, decarbonizing energy, direct carbon production at the production process by CCUS, and transport, construction and process time, how much it has to be reduced. The same thing which has been I projected over here is represented in the form of a. Same is the case with the steel. Steel also, I think it's possible for us to reduce the similar to that of the concrete, as you can see here. This is for the steel, the production, how we can reduce the carbon dioxide to the environment by 2070 in India in phases, 45% by 2030, 100% by 2070. This is what the proposal is. By doing that, if it is possible with this proposal for us to achieve this carbon neutrality by 2070, I think only by getting this net zero in the steel as well as the concrete construction, I think we'll be able to completely bring down this carbon dioxide emission to the environment by 2070 in the built environment. Also, as you can see from here, that the policymakers have a big role to play. During the whole life cycle here, I have divided the responsibility of the different stakeholders. Whatever is shown here, the primary responsibility, and this color is a secondary responsibility, yellow is the tertiary responsibility. The policymakers, if you can look at here, have the responsibility from cradle to cradle. If you really look at for the cradle to cradle boundary system, as you can see here. Similarly, the designers have the cradle to cradle boundary system. The designers have the private responsibility. Some cases it is a tertiary responsibility, some cases it is the primary responsibility, and some cases again here the secondary responsibility have. The policy makers as well as the policy makers as well as the designers play a very, very important in achieving the carbon neutrality. What are this? In fact, unfortunately, in India, we don't have the carbon factor, carbon inventory for carbon as well as the energy inventory for the sort of, which is a sort of a ratified carbon as well as the energy factor inventory, which is available. First step is to make sure that we get this carbon factors for all the construction materials. The repository for carbon and energy inventory, which has been got from the suppliers, designers, builders, owners, and also there are some, collaborating with the various institutions, like I told you that I stressed that the EC3, Econwell, and also the equipment maker. And if it can be compiled in some place after getting it certified in a place, say for example, in the Ministry of Environment and Forest, and if it's available for us, we will be having a real status of the carbon inventory in India, whether it's energy inventory or the carbon factor inventory. There are world over, there is something called the environmental product declaration. It has to be made, it has to be brought into the regulatory framework, basically. And I see Mr. Dr. Anchuri, I've got another 15 minutes if it looks like, right? I don't have 6:24 now. Dr. Anchuri? I think he's not there. So another thing is it has to come in the policy itself. Basically, the policy itself, it has to be, the policy could be the 2CSPS system, quality. Right now, our procurement strategies is based on, especially in the infrastructure, in building sector, it has to come yet, in my opinion, quality cost-based system. Whereas 70% importance of the weightage is given to the quality, whereas the rest is given to the cost. We have to move into this quality, cost, and sustainability based system from the QC SBC system, where the percentages, the weightages could be 40, 20, 40. 40 for the quality, and cost is only 20%, and the 40% for. Whereas in the tender documents itself, threshold limits of the carbon dioxide emission to the environment could be specified. We'll have to move into that. So policymakers have, even the standards and quotes making committees, have a lot of important, a role to play. And you'll have to review the safety factors, unless safety factors have been built in. Our idiosyncrasies of the code makers and the standard makers in this country is that our standards and code makers, that the construction deficiency have to be factored in factor of safeties, should not have any place. That sort of thinking should not be there. No workmanship failures can be covered by the construction factor of safeties which has been inbuilt in the design. So we need to have a look at the partial safety factors to make our structures less massive. In the sense, it is very massive, and the quantities are quite lot, emitting a lot of carbon dioxides. And also there are many things like the 40 mm and down aggregate has the potential of cement saving that we should be encouraged. And there are slag aggregates and copper aggregates and aluminum slag aggregates. This has to be used. The IS 383 is a very good way forward that they have been doing it. And there should not be any restriction in the use of the mineral admixtures like slag as well as fly ash. Basically, all of us are aware now, it's a fly ash as well as the slag as a replacement to OPC to reduce the carbon dioxide can be used very extensively. There are restrictions to use that. I think those sort of restrictions of the amount of the carbon dioxide, the mineral admixture used to be this one. There are other specifications which is unsustainable or not carbon friendly. That like the factor of safety for the pile capacities and the use of lazy formula for the calculation of the score depth, insisting that the caps, pile caps, as well the well caps have to be around 10 meter or 12 meter below the ground level. And these are the sort of things. And there is also a case study in one of the cases. There are two bridges which you can see here. This is the existing bridge. New bridge was being done. There are around 28 foundations, well foundation of around 40 to 50 meter. And one of the clauses in the foundation code is the depth of the foundation shall not be less than those of existing structure in the vicinity. It's almost around 80 meter. In the revised design, it was possible for us to take this foundation 10 meter above, than the existing foundation over here. And this 10 meter into, it's a massive foundation, and the concrete consumption also is very heavy, and it can emit a lot of carbon dioxide emissions. So this sort of the clauses in the higher codes has to be really looked into. Another case is, the using this Lacy's equation, if the score depth has been calculated after for 20 years, the depth of the foundation has been reduced by 20 meters. These are the sort of things we need to look into. Another area is some of the codes does not permit the use of the mineral admixture itself, especially in the railways. What I see is, and for a massive construction, mass constructions like this, not to allow the mineral admixtures like slag, fly ash, to reduce the carbon dioxide emission. Not only to that, even to make this the structure less crack prone, because if you use a lot of OPC, there's a heat of hydration and the structure is vulnerable. It's a crack prone structure, so we'll have to allow that. Some of the codes make sure that the mineral admixtures not allowed. And also going for, like always it is insisted you have to go for the glued construction, epoxy glue. There are a lot of failures are taking place. All of you are aware during the construction of the bridges, and it is because of the improper application of the epoxy, as you can see, as it has been reported. And if you go by the dry joints instead of the epoxy glue, epoxy application and the external pre-stressing, it is possible for us to save the time period because of the less operation of the epoxy application, and also the saving in the epoxy, which is a carbon product, once again emitting the carbon dioxide to the environment. It's possible for a 10-kilometer viaduct to save around 1 year, and also the carbon dioxide emission will be reduced to a large extent. And the accident will not take place if the epoxy glue application, since the epoxy glue application is avoided over here. So these are the sort of things we'll have to really look at. Another area where I would like to highlight is the policy makers of the different departments have to come together. They have to have a bent of a mind for the carbon dioxide, carbon footprint reduction, because the sustainability is a very hotly discussed topic, and it's a moral and ethical responsibility of all of us, all we engineers. Just imagine this MTHL, like this almost around 24-kilometer, the highway bridge over here. And we'll have to make sure that the multimodal transportation is made. After some years, we'll have another railway lane or a metro lane just beside it. And instead of having a double-decker kind of a situation where both the train, traffic as well as the highway traffic can go on, this 24-kilometer, again, the foundation as well as substructure has to be done. So all these policy makers have to come together and make sure then again this sort of things will not happen. That is the reason, if you really look at the China, where the bridges are crossing very wide rivers, they invariably are going for the multimodal transportation. Below the trains, on top of this, basically the highway construction goes on. So the policy makers have to come together and making these policies. And designers and contractors' role in decarbonization is very, very important. See, so many accidents have taken place, and we'll have to make sure these accidents are reduced. Imagine an accident taking place, that facility has to be replaced. This is a spike in the carbon dioxide emission to the environment, basically. And also the time overrun as well as the cost overrun, in addition to the casualty and the injuries to the people. So the safety has to be given an utmost importance. Design. Like we do the value engineering, by doing the value engineering, when you are doing the engineering and designing, almost around 70% of the cost of the project is created. The engineers as well as the designers create 70% of the cost. So if you're doing the value engineering during that stage, even if you save around 20% out of the 70%, we'll be able to save the cost quite a lot. Similarly, the carbon value engineering has to be done. We have seen product stage almost around 40 to 50% of the carbon dioxide emission takes place, and in use stage again around 40 to 38 to 50% carbon dioxide emission takes place. So the carbon value engineering has to be done during these two stages extensively. because during the construction stage, hardly, 1 to 2%. In fact, it may go up to 4% in some cases. And during the demolition stage also, it's around 1 to 2%. So the value engineering has to be extensively done during the product stage as well as the in-use stage, as you can see here. That concept has to be developed. And the design efficiencies for the concrete structures, I think I'll just note it down here because of the paucity of the time. I'll just go faster. Similarly, for the steel structures as well as the concrete structures, I'll give some illustration over here. Now, the use of slag as well as the fly ash is well understood now by all the civil engineers and structural engineers, and the majority of the OPC is being replaced by slag or a fly ash in our country. Even in some cases, the aggregates, fine as well as the coarse aggregates of the slag has been used. In some cases, the fly ash also has been used. But going forward, this only the 15% of the slag as well as the fly ash is available. I think we'll have to go for the alternative pozzolanic material like the calcined clay. I think it's available in abundance, and also the what we call it as a bauxite red mud waste that is there. I think valorization of that and the use of that has to be explored as a replacement to the OPC cement going forward. Replacement of the rebars as well as the steel strands with the AFRP strands as well as the this one I have already explained over there. And to reduce this carbon dioxide in the emission in the in-use state, that's service state, I think we'll have to design for a durable structures, the performance-based design, especially in the carbon as well as the steel can be resorted into, and the resilient structure. I think we'll have to come out with, because of the climate emergency, the sea level is rising and the floods will be unseasonal, the cyclones will be unseasonal. I think we'll have to have a separate, we'll have to develop the probabilistic models for taking into consideration all these climate emergency effects, and to make sure that structure doesn't require much interventions as well as the replacement during its lifetime, as you can see here during this 100 years. The performance should be up to 100 years so that the interventions as well as the maintenance is not required much. And this is a classical case in use stage. What I'm talking about is one of the bridges. After 50 years, it had to be replaced. Superstructure had to be replaced. When it is to be replaced, naturally the steel superstructure was resorted to because the same foundation was used here. It's a prolonging the life of the bridge concept has been used over here. But if for any reason, if the bridge has to be replaced over there, this problem will be there. The spike in the carbon dioxide. Yes.
Sir, sir, small request, sir.
Yes.
Shall we conclude in 10 minutes, sir? Because at 7 o'clock.
Yes.
We have another
I will do that. I will do that. I will do that.
Okay,
so
okay. Thank you. Sir. Sorry for that.
No problem. So in case of the buildings, it has been seen that the 10% of the foundation, 10% of the carbon dioxide emission takes place in case of the buildings for the foundation, where the 90% carbon dioxide emission takes place in the superstructure. And as a system of the construction, it has been reported by Abhijit Kulkarni et al. The wafer slabs are more efficient for RCC element for the slab, while PT slab is also comparable, and the M40 grade of concrete is most optimum. That's what has been done. As far as the replacement to OPC is concerned, also the arch structural form, as all of you are knowing, that it is subjected to the compression, as far as it's not subjected much to the flexure, as far because of which the crack it is not much crack prone. I think that is why you see the arch structures all over the world lasting for a long time. I think perhaps it's arch forms can be used as far as possible. Pre-stressing also gives a lot of advantages in bridges, and the new materials like high performance concrete, that up to the strength of even 120 to 150, with the high tensile steel up to the strength of even 780 MPa, it can be used as a composite material in case of the bridges, as you can see here. And the quantum of the material which has to be used, which has been emitting the carbon dioxide, can be reduced to a large extent. That is another way. Even this the steel up to the strength of 700 NTM, 780 MPa, and UHPC composite materials can also be used in the buildings. By using that, your sections will become slender, you get more spaces, and those sort of things also will reduce the carbon dioxide emission, and also you will get a lot of space for that. Vertical height is reduced. Because of the vertical height is reduced, vertical operational energy, because of the operation of the vertical systems, which is energy is required, is reduced. That is how it is possible for us to. Orthotropic plates compared to that of like a regular RCC system with the composite system will reduce the RCC slab also to a large extent. Structural steel, all of you know that can last for a long time. It's a myth to understand that structural steel is a highly corrosive material. Most of the bridges in India which have been using structural steel is been lost for a long time. And there could be a wonderful structural steel bridges that, as you can see here. And also it could be aesthetics. Right? Also there are some myths among the people. They think that the structural steel cannot be made aesthetically looking facility or an artifact. As you can see here, some of the outstanding bridges which you can see on the screen is because of the using the structural steel. Using a very high tensile steel, it's possible for us to reduce this quantum of the structural steel itself. By reducing the quantum of the structural steel, indirectly you are reducing the carbon dioxide emission to the environment also. And we can switch over to this stainless steel. Stainless steel, it's in Visakhapatnam. I think that should be of interest to this one. This is a FOB in Visakhapatnam making use of the stainless steel, and it requires less intervention during the also the maintenance. That in use stage, always the carbon dioxide emission is 38 to 60%. Weathering steel, again, it doesn't require maintenance, which can be used extensively. And modular accelerated construction also can be used. This is very important because I will come to the modular construction later. Now, reducing the carbon by upgradation of the plants and reformulation of the product mix. In steel, you can see that the steel production always, if you're using the electric arc furnace instead of BOF, it's possible to reduce this embodied energy in the steel to a large extent. And if you use the recycled steel instead of the primary steel, again it can be reduced to a large extent. Similarly, the heat which is produced as a waste, both in the steel as well as the cement production, that heat can be reused for the purpose of another power requirement. That can be reused by, that is called the waste heat reduction system, waste heat recovery system. That can be used, and that can be also used as this one. So decarbonization is very, very important. Basically, the decarbonization in the sense you can renewable, non-renewable source of energy has to be replaced with the renewable energy sources, and also the energy which is used, the heat which has been wasted, it can be again used to produce the heat again without using the additional energy. The energy consumption can be brought down by 30 to 40%. That's what it is said. Last stage is setting up circularity, setting up by circularity. Whatever is estimated, which cannot be avoided, which cannot be reduced, ultimately we'll have to set off that carbon dioxide. How it can be used? It has to be designed. Steel, as far as the concrete structure, has to be designed. It is such a way that after the 100 years use or the service life use, it should be easily deconstructible. It should be easily recyclable. It should be easily reusable. It should be easily recoverable. And it should be, the design has to be done such a way that, like if it's required, widening of the facilities has to be done. Say, for example, if the building is done to increase the capacity of the building, you may have to give the provisions to provide the multi-story, some more heights of the building can be done later. That sort of scalability has to be done. So the design for circularity is very, very important. The modular construction as per the pre-engineering construction. Say, for example, If the modular construction is there, say for example, if it can be made use of the UHPC, ultra high performance concrete, say for example, after the 100 years, in case of the 50 years, these same components can be dismantled, again reused for that purpose. Then it doesn't emit the carbon dioxide to the required level. Similarly, the pre-engineered structures, it can be dismantled, again reused for the construction purpose, which will reduce the carbon dioxide to the large extent. Also, whatever cannot be, carbon dioxide emission cannot be reduced even. The only thing is that has to be captured in some technology, using some technology, and that has to be done. And that captured carbon can be used for curing aggregates, carbon fiber, polymers, fuels, DME, SAF, ethanol. This captured carbon can be converted and again it can be reused. And whatever the carbon which cannot be reused again, it can be stored in the earth itself, or Mother Earth, in the saline aquifers. India has the capacity to store this carbon dioxide emission up to the 600 gigaton. All over India, you can see you have got the saline aquifers, the west, north, south, as well as the east. That can be done. This is how we'll be able to achieve this carbon neutrality in the steel as well as the construction, steel as well as concrete. In my opinion, if it's possible for us to achieve the concrete, the carbon neutrality in the steel as well as the concrete, I think we'll be able to achieve the carbon neutrality in the built environment. Thank you very much, Dr. Venkata Subbaiah, for allowing me to take, in fact, some more time than you desire. Thanks a lot.
Thank you, sir. Thank you very much, sir. Excellent lecture you have given, sir. You have started with green mean temperature, how it is and why it is increasing, and what is the importance to maintain this DMT about 1.5 degrees centigrade, sir. And today I have come to know through different technologies, sir, like carbon. So many times I used to say about CO and CO2 like that. But today you told what are the differences between operational carbon and embedded carbon. The first time I have come to know the difference between these two types, sir. And you very well explained about the model for carbon neutrality and extensively explained about the global strategies for net zero steel and concrete construction, sir. It is very interesting and detailed lecture we had, sir. Thank you very much for you, sir, for sparing your valuable time and giving the valuable information for the audience, sir. So many people are watching in a groups, and also live streaming is going on, and I think all the participants have been benefited with your rich knowledge you have given by your talk, sir. Thank you very much, sir.
Thank you very much. Thank you for the opportunity.
Sir, in fact, there are many questions, and in the meantime, when they ask the questions, you went on answering them. So we will not take up those questions because they are all. But any specifically, if you have any things, they can ask with the permission of chair. But just one question from my side. So because I am into the building sector. So in building sector, 90% of the buildings are in a private or public sector where we can influence. But infrastructure, which is a major chunk of thing, so it's a very challenging to make them understand the sustainability, and it's a very big process, and a very small thing also. It's a protocol. So how the challenges in the private and the public sector normally the approach should be?
Yeah. See, my whole thrust today was Dr. Anchuri. I just want to differentiate between the building sector as well as the infrastructure. In building sector, 27% is carbon dioxide emission takes place because of the electricity consumption. For running this, like your lifts and running these bridges and lighting in the houses and those sort of things. That's basically takes place. Whereas the infrastructure, the operation carbon is not much. It's almost, I should say, it's negligible. But in infrastructure, in use stage carbon, because of the maintenance and the interventions which is required for during the 100 years, the replacement has to take place, rehabilitation has to take place. that carbon. So it balances out the operation carbon in the building sector as well as the new stage carbon in the building sector. It automatically comes down between 38 to 40, 38 to 50%, 38 to 60%. That's what it is said. Now the question is, as far as the private sector is concerned, I think a lot of work is being done. Green certification is going on, and your architects, as far as your structural engineers, are give a lot of importance to whether it's a commercial, residential buildings, even other places also. But when it comes to the public sector, the policy making is very important in case of the infrastructure. Unless this threshold limits for the carbon is specified in the tender documents itself, I don't think anybody is going to do that, because anybody is going to give attention to this sustainability and carbon neutrality. That is why in the tender documents, as well as the codes and standards, has to be made in such a way that it's always sustainability oriented. There are a lot of provisions in the codes and standards actually, which is not sustainability oriented, or the carbon friendly specification. That we will have to really look into. I don't know whether I have answered your question.
Yeah, you answered the things, but we have some questions in the query before we conclude and go for further. Sir, today is the safety day also. So some people are asking the failures versus sustainability in few one or two sentences. So are the sustainable structures are more safe?
Yeah. See, basically, I think this concern is very valid, and especially in bridge construction, all of you are aware of the failures have been during the construction, especially have been happening unabated, especially precast segmental construction, which has been taking place continuously. Imagine any bridge failure taking place during the construction. During that period, if it fails, that part of the bridge has to be replaced, and not only that, there is a time overrun as well as the cost overrun. Whenever there is a time overrun and the cost overrun, it's always related to the carbon dioxide emission also. I can tell you that as it gets prolonged. It is very important. We will have to make sure that even during the construction, the failure doesn't take place. The replacement of that bridge portion which has been done, the investigation will take place. For the investigation to be completed, it will take 1 year, and that facility will not be there. Not only since the facility is not there for 1 year, the user utilization carbon also will increase, because the traffic has to go from somewhere else, and the construction is going on. Traffic diversion will take place. Because of that, the user utilization carbon also will take place. It is very well related. In fact, the carbon dioxide emission because of this failure may double, in my opinion, if the failure takes place during the construction. So it's very important. Very durable structures are designed. Also, the safe structures are designed during the construction.
Mr. Sitaram.
Thank you, sir. Thank you, sir. So now I request Dr. K. Sitaram Babu Garu to propose vote of thanks.
Thank you.
Sir, thank you very much, sir. Hegde, sir, such a towering personality, sir. You are former executive director, Gemon, former CEO, setup and founder of Decon Complete Solutions. Sir, your lecture, I think probably we're hearing it for second time, sir. I think you have got the lot of people would like to listen to you, sir. As we said earlier, we would like to come back to you again, sir, during our one day or 2 day seminar, sir. Thank you very much for your wonderful lecture, plus the time that you have given for us, accepting our invitation, be part of it. I thank the chairman, Dr. G. Venkat Subbai Garu, and the convener of the event, Dr. S.P. Anchuri Garu, for having made this event a reality, sir. I also thank Brahma Reddy Garu, the past chairman, and also Dr. Rameshwara Garu, or another past chairman, to be part of this event, sir. I also thank Rama Garu for the committee member of the Telangana State Center for having part of this event. I also thank individually many of the members who are part of this, sir. One and all for having part of it and made this event a grand success. Before we wind up, sir, I would request all of you to stand for the national anthem, sir. Thank you. Thank you very much.
Thank you.
Can we sing it?
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय जय जय
Jai Hind.
Jai Hind. Thank
So
you very
thank
much.
you for all of you. Now I request all of you kindly join for another program on National Safety Day.
Thank you.
Thank you, sir.
Doctor.
Thank you for all
Thank
of
you, Hegde ji. Namaste.
Thank you.